So we talked about delta H, which we know is enthalpy, and delta S we now know is entropy. And we know that they both play some role in determining if a process is favored. So we know from the beginning of this note set that if a reaction is exothermic, that means the delta H value is negative, those reactions are favorable. And if the reaction produces more disorder, or the delta S is positive, those reactions are favorable. So if delta H is negative and delta S is positive, then we can say that the reaction is favorable for sure. But what if delta H is positive and S is positive? So like one of them is favored and one of them is not. Or what if delta H is negative but delta S is negative too? So one of them is favored and one of them is not. How do we determine if the process is favored or not if these two things are not true? So we'll work through some examples about how to decide. This is our main goal in talking about delta H and delta S, is we need to be able to determine if a reaction is favorable or not. We have two methods for doing that. One is by looking at the entropy of the universe, because we know from the second law of thermodynamics that the entropy of the universe is always increasing. So if our process increases the entropy of the universe, then we know it's favored. Another thing we can look at is the delta G value, or what is called the Gibbs free energy. So first we'll look at the delta S of the universe. The universe, remember, includes the system and its surroundings. So the delta S of the universe is equal to the change in entropy of the system as well as the change in entropy of the surroundings. And if the change in entropy of the universe, so both of those added together, if both of these added together create a positive delta S of the universe, then we can say for sure it's following the second law of thermodynamics and it is a favorable process. How do we know what the delta S of the surroundings is? How do we figure that out? Well, it's related to the delta H value. If the delta H value is negative, that means the process is exothermic, right? Well, if the delta H value is negative, that means that the system is giving off heat. And remember, when the temperature goes up, that makes the delta S value go up as well, because the particles are moving faster. So an exothermic reaction is going to increase the entropy of the surroundings, because it's giving the surroundings heat, which causes the molecules to move faster. So if delta H is negative, the delta S of the surroundings will be positive. However, if delta H is positive, that means that the surroundings have to give heat to the system. So that's going to make the surroundings cool off. And we know when the temperature goes down, so does the entropy. So as the temperature goes down, the delta S value will decrease. So it will be negative. So these two things are opposite in sign. If the delta H is negative, the entropy of the surroundings, let's be clear here, we're not talking about the system. We don't know what its delta S value is just yet. But if the delta H is negative, then the delta S of the surroundings will be positive, and vice versa. Therefore, if we go back to this main equation, if we have a positive delta S system and then a positive delta S surroundings, then we most certainly have a positive delta S of the universe. Now, how do we get a positive delta S of the system? That's going to be a process where the entropy of the system increases. That could be a process that makes more molecules. That could be a process that changes phases. That could be a process that increases volume. Okay, there's a lot of ways that we looked at before that the delta S of the system could be positive. And if the delta S of the surroundings is also positive, that means that the process must be exothermic, or the delta H must be negative. If these two things are true, then the process must be thermodynamically favored. So if delta S is positive and delta H is negative, that makes delta S of the surroundings positive. Then delta S of the universe will be positive, and that must be a favored process. But again, if one or the other of these is not positive, one of them is not favorable, we've got to figure out which one's higher to determine if the delta S of the universe is favored or not. So let's look at another way to determine if a process is favored or not, and that is the Gibbs free energy. This is the method we're going to use 99% of the time to determine if something is favorable. Gibbs free energy, delta G, is measured in kilojoules per mole. Okay, and again, on each of these, should have a per mole. Per mole, per mole, per mole. We can add those in. So the delta G, again, is the free energy change for a reaction. If it is negative, then that means the reaction is giving off energy, and that will be thermodynamically favored. So our delta G ultimately tells us if something is favored or not, because it considers delta H and delta S. So we have our delta H value. Remember, it'll be positive if it's endothermic, negative exothermic, minus the temperature in Kelvin times our delta S value. Notice here the unit on delta S has to be kilojoules to match delta H and delta G, but they will not give you delta S in kilojoules most of the time. So remember to change your unit, and also remember to put your temperature in Kelvin. So what we can do is if we have delta H or delta S, and we really need both, we can use that to calculate delta G. If the delta G value turns out to be negative, then we know that the system is favorable, and if it's positive, we know that the system is not thermodynamically favorable. Okay, here this is in different words. So we have the delta G, that's the maximum amount of energy that we can get from that system to do work, known as the free energy. Delta H is the energy transferred as heat. Remember, that's related to Q. And then the delta S and the temperature are the energy we can use to create disorder or randomness. Again, if that delta G is negative, we're looking at a favorable reaction. We can't base it just on delta H and delta S. We have to base it on both of them to decide. So how do we find delta H? We have that equation that we just looked at, or we can also calculate it using delta G of formation values. Calculating delta G. So when we're using the equation that we see on number 1, we have delta H, which we know so many ways to find from lesson 2. So we can calculate delta H using any of those methods. We can calculate delta S using products minus reactants. And then we can use those two to calculate delta G. Now sometimes they're really nice and they'll give you delta H and they'll give you delta S, and you just need to calculate delta G. And on a free response problem that they're trying to kind of pull more out, they'll make you calculate delta H, calculate delta S, and then use that to calculate delta G. You cannot tell if something is favorable just from calculating delta H or just from calculating delta S. You've got to know both in order to determine if it's favorable. You can also calculate delta G directly using delta G formation values, and we'll look at that in a second. So here's an example. Calculate delta G for this reaction, and they give us the delta H value and they give us the delta S value. Now they're missing their per moles, so you want to make sure you write those in. Is this reaction favorable? All right, well first, before I do any math, let me see what we've got here. We have an exothermic reaction, so that's favorable. And then we have a delta S value that is negative, so that's not favorable. So we have a favorable condition and a not favorable condition, so I'm going to have to calculate and see how delta G turns out. Watch your units here. This is joules, and that one's kilojoules, so I'm going to move my decimal 3 places to change that one to kilojoules. I've got 32 degrees Celsius, so I'll add 273 to that to get my Kelvin. And then I can calculate delta G using delta G equals delta H minus T delta S. I plug those in and I find that delta G is actually positive 15.3 kilojoules, and that is not thermodynamically favorable. However, this process may be favorable at a different temperature. Remember, temperature plays a key role. So the question is, at what temperature does the reaction become favored? And we're going to assume that the delta H and the delta S values do not change when the temperature does, although in fact they probably do vary some with temperature. When we ask this question, what we're asking is, when would delta G become negative? Because currently delta G is positive, and that's not favorable. So when would it become negative? That is favorable. So to determine this, we're going to set delta G at 0, because 0, right, is the breaking point between positive and negative. So we set delta G at 0, and then we plug in delta H and delta S to solve for T. Watch your units, make sure your kilojoules are there for both so that they cancel. And we find that at 285 Kelvin, this process would become favorable. If we look back at the first example, it was at a temperature of 32 degrees Celsius, which would be 305, I think if I'm doing my math right, 305 Kelvin. And this is saying at 285 Kelvin, it becomes favorable. So that means for this reaction, when the temperature drops, the reaction actually becomes more favorable. Here's a table to summarize the favorability of a reaction. If your delta H is negative, which means it's exothermic, and your delta S is positive, which means the entropy of the system increases, that process will be favorable no matter the temperature. The opposite is true. If you have an endothermic reaction where the entropy of the system decreases, like in the second row, those processes are never favorable, no matter the temperature. However, if you have the same sign on delta H and delta S, that's going to mean that one of them is favorable and one of them is not. And if that's the case, then the temperature will determine whether or not the reaction occurs. If both of them have a negative sign, those processes are favorable when the temperatures are low, and they are not favorable when the temperatures are high. And the opposite is true if both of them have a positive sign. Now, the temperature at which it becomes favorable is different for each reaction. And if asked to find that, you would calculate it like we did on the last example. Set your delta G value to 0 and then calculate T. Here's another example where we want to know if this process is favorable or not. Before you ever do math on these questions, check your signs on delta H and delta S, because sometimes you can figure it out without actually calculating delta G. Now, if they ask you to calculate delta G, of course you want to do that. But sometimes we can figure out and answer the question, is it favorable, without doing the calculation. Here we have a delta H that is negative. That means that this process is exothermic, and we know that exothermic processes are favorable. And we have a delta S for the system that is positive, which means the entropy is increasing, and we know that is favorable. So we have two favorable conditions. I can say for sure that this reaction is favorable, and my justification is because it's exothermic and the entropy increases. Also, if I look back at my table, it says that if delta H is negative and delta S is positive, that is favorable at all temperatures. So I don't need to do any calculation to say that this is favorable because those two conditions are met. Another way to calculate delta G is using those delta GF values. And that's going to be the same equation as delta H and delta S, products minus reactants. Just like delta H, if something is in its standard state, its value for this delta GF, or formation, is 0. Because remember, it's already there. It's already in that state, so it doesn't require any energy to get into that state. So it just has a delta GF value of 0. Remember, this is not true for delta S values because everything has some disorder to it. These values, again, you would either be given or could just look up on a table. And products minus reactants, remember your coefficients would lead you to the response. Here it asks you for the delta G for the reaction. This is known as thermite. So you've got your iron oxide or your rust reacting with aluminum to form iron and aluminum oxide. So to calculate the delta G for the reaction, we would need the delta GF for aluminum oxide and 2 times the value for iron, minus the reactants, 2 times the value for aluminum and 1 times the value for iron oxide. Now we know that aluminum and iron are going to have 0 values for delta G because they're in their standard state, solids. So you can see they pulled the numbers here from some table. So here's the value for aluminum oxide, and here's the value for iron oxide. You see the subtraction sign. You also see the coefficients. Now they don't really matter here because we're multiplying by 0 for those, but if you have a coefficient, don't forget to include it in those calculations. Once this calculation is done, the delta G value turns out to be negative, so I can say that this reaction is favorable. Another reminder of what I said earlier, when we say that a process is favored, that does not mean that it is fast. The rate of a reaction is determined by something called kinetics, and that's a later chapter, not thermodynamics, which is what we're talking about in this unit. Many thermodynamically favored processes do not occur at a measurable rate. For example, oxidizing. That's the process of rusting. It is thermodynamically favored. However, if you have a large iron beam in some building, it may take years, even hundreds of years, for it to rust away. So, just because something's favorable does not mean that it's fast. Keep that in mind. So what do we do if we find out that the delta G value for a process is positive? We find out that it's not favorable, but we still want to make that process go. How can we use some other source of energy to make a process occur that is not favorable? One example is using electricity. So all the time we use electricity to run processes that aren't naturally favorable. For example, recharging a battery. A battery does not simply recharge itself. A battery uncharges itself, right, to produce energy, but it's not going to recharge itself. But we can use electricity to make that unfavorable process occur. Photons, mainly from the sun, can supply the energy we need to remove electrons from atoms and therefore supply the energy we need to make a chemical reaction go. For example, in photosynthesis, we have a process where we change carbon dioxide and water into glucose and oxygen. That process has a delta G value of positive 2,880 kilojoules per mole. That process is not favorable naturally. However, we have lots of energy coming from the sun that can disturb the electrons in the atoms and initiate that process. So just because something's not favorable doesn't mean it can't occur at all. It just means we need some outside source to kind of push it along. So that outside source could be some source of energy like the sun or electricity. Another thing that can occur is something called coupling. So when this is kind of the opposite of photosynthesis, when our bodies start to break down this glucose, we think of breaking down glucose as a change that's going to give us energy, right? It must be favorable because it's happening inside our body all the time. But in fact, the first step of breaking down that glucose actually requires 13.8 kilojoules per mole of energy. So how does our body make it happen? Well, it does what is called a coupling. So it couples that reaction with the breakdown of ATP. And we know that that's a positive process, or a favorable process. It actually has a negative delta G. And that energy that's produced from that process can then fuel the initial breakdown of glucose, and if you put them together, the overall delta G is still negative. So we can couple a non-favorable process with a favorable process. As long as the total delta G value is still negative, then the overall process will be favored. So those are some ways to make non-thermodynamically favored processes still go. And our bodies use those, and then we use those with technology as well. So I hope that's been informative. What you need to know for sure is what determines if a reaction is favored or not. That's going to be our delta G or our delta S of the universe. And then what two factors play into that? That's our enthalpy and our entropy. So make sure you can determine via calculation or via some reasoning whether or not a reaction is favorable. And that's going to wrap up thermodynamics unit.